During the COVID-19 pandemic, mathematical models of the disease have shaped lockdowns and public policies. These models are vital as there is simply no other feasible way to study and understand the massive scale of infectious diseases without them. As mentioned, these models can project and predict how infectious diseases are likely to spread, which is used to help inform public health interventions such as lockdown measures. The epidemiologists creating these models therefore carry a huge responsibility as their work can affect the life of millions. So before we dive into the complexities of modern infectious disease modeling, it's necessary to understand the basics of how these models work. Models use basic assumptions or collected statistics along with mathematics to find parameters for infectious diseases, such as the R number or reproduction number, which describes the ability of a disease to spread. For those of you who have never heard that term before, the R number describes the average number of people that one infected person will pass on the virus to. COVID-19 has an R number of approximately 3 if no action is taken to slow its spread. If R is greater than 1, the disease will spread. If R is less than 1, the disease will die out. If R is equal to 1, the disease will continue to infect the population, but not increase or decrease. Right, so by finding these parameters, epidemiologists can calculate and predict the effects of various interventions, such as regional lockdowns or vaccination programs. These predictions help governments decide which interventions to implement or can serve as a warning of which to avoid. Now, this sounds simple, but in reality, infectious disease modeling can be extremely complicated and face several limitations. All models are wrong, but some are useful. Statistician George Box supposedly once said, a phrase that has been often repeated. This is because these models are often based on several assumptions, and should these assumptions be faulty or incorrect, then the model's usefulness and accuracy decreases. Some examples of common base assumptions are 1. Rectangular and stationary age distribution. This assumption assumes that every person in a population lives to the same age and there is an equal number of people for each age. While this makes sense for developed countries because of their better health conditions and lower birth rates among other factors, it's not always the case for developing countries. 2. Homogeneous mixing of the population. This assumption assumes that the interactions between people in a population are completely random, but this is rarely true because of how society is structured. For instance, people in Toronto are more likely to interact with Torontonians, and the same applies to other groups such as high school students or the Italian community. What makes this assumption useful, though, is that it makes math more easy to deal with. These models can be further limited when they fall short in attempting to project or incorporate multi-strain infections, infections with time-varying infectivity, and diseases or environments where superinfection is possible. So obviously, there isn't just one type of epidemiological model. These models can be classified into categories based on how they deal with factors and assumptions such as variability, chance and uncertainty, time, space, and the structure of the population. Generally speaking, models can be classified into one of 3 classes: statistical, mathematical mechanistic state space, and machine learning-based models. In simple words, statistical models use regression and multivariate techniques to help us rapidly assess emerging epidemics through surveillance, early detection, and identification of patterns. Mathematical mechanistic models are often in the form of differential equations, partial differential equations, or agent-based simulations, and most often describe the dynamics of epidemics in the population. Over the last years, machine learning has become a promising way to data mine personal behavior. We won't go into too much detail about machine learning and epidemiology, but if that's something you're interested in, let us know in the comments what you learned about how machine learning can be used in epidemiological models. So before we finish off, we'd just like to review a type of epidemiological model so you can see how they actually work and look like. One of the most common models is the SIR model, which is a compartmental model that computes the theoretical number of people infected with a contagious illness in a closed population over time. It consists of a simple system of differential equations. Here's an example of an SIR model, where S stands for susceptible, I for infected, and R for recovered. The SIR model uses differential equations, like some of the ones you see on the right. This model operates on two base assumptions. 1. No one is added to the susceptible group because we ignore births and immigration. The only way an individual leaves the susceptible group is by becoming infected. 2. There is a fixed fraction of the infected group that will recover during any given day. Strictly speaking, an infected person must be capable of spreading the disease to a susceptible person. A recovered person can still feel miserable and might even die later from pneumonia. As you can see, this presents a limited model since the SIR model assumes that every person is moving and has equal chance of contact with each and every person, and it assumes that the transmission rate remains constant throughout the period of a pandemic. Even those who have been tested and quarantined are assumed to behave the same way. In this specific model, the R value is 2, which means that every person infects 2 people on average, and the virus is spreading. The I value is 10 to the power of -5, which represents the initial concentration of infected individuals. As one of the most basic compartmental models in epidemiology, we hope that this brief explanation helps you get a better understanding of the spread of infection. Thank you so much for watching to this video. Next time, join us to learn about how you can put your data science and public health interests to use and pursue a career in epidemiology. If there's anything else you'd like to see us cover in the future, please let us know in the comments below.